In this lecture, I also want to introduce two concepts related to receptors and how they interact with drugs. The first one is desensitization. Desensitization happens when um, a receptor ceases to respond to a certain stimulus that is repeated or chronically exposed to. For example, when a drug is administered continuously. So from the mechanistic standpoint, we can talk about desensitization in two or three main categories. One is that the receptor becomes uncoupled from the downstream signaling, and so although the ligand is binding just fine, nothing happens downstream. Another possibility is that the receptor gets internalized by endocytosis and thus decreasing the concentration of receptors that are available. And the third possibility is that simply the receptor is not expressed or synthesized as much, and so we have a reduction in total number of receptors on the cell membrane. So these three mechanisms contribute to make the receptor and, well, rather the cell unresponsive to to the ligand for the receptor. The opposite of that is the sensitization mechanism, when receptors can become sensitized upon long-term exposures to antagonists. And this is a very important problem because it will factor in how we treat dependency to opioids. For example, if we have a receptor that interacts with the neurotransmitter here, normally we'll have the response elicited by binding to the receptor. In the presence of an antagonist, what we'll have is that no response is possible because the natural ligand cannot bind to the receptor anymore. So the cell may respond by increasing the synthesis of the receptor so that we have more receptors expressed per membrane unit. And so in that case, then the presence of increased concentration or of this neurotransmitter can basically outcompete the antagonist. And so we have a response, typically reduced compared to the normal response, but still present. So as we increase the concentration of antagonists, what we have is that once again we abolish the response. And so we'll need more antagonists to abolish completely the response. Now, let's say that for some reason we stop taking the antagonist. Well, all of a sudden we'll go from a situation where there is no response because all the receptors are occupied by antagonists to a situation where we have an excess response because now all the receptors are bound to the ligand, to the agonist, and there are more receptors on the unit cell. So these two phenomena are very important and were basically codified in reference to the opioid receptors. And so if we look, for example, sensitization, that's what happens oftentimes with treatment of opioid addiction with something like methadone, which is a weak agonist and basically works as an antagonist. And so when a patient is treated with methadone, we're going to be in this situation where even in the presence of the drug of abuse, we'll have no response. However, if the patient ceases to take methadone, what we'll have is that we'll have excess response because there are more receptors now expressed on the cell membrane. And unfortunately, this is also the physiological base for the phenomenon of overdose that is often observed in patients who are relapsing from treatment of addiction. And so, they will stop taking methadone, take heroin, for example, and increase the response. Okay, In the last part of this class, I want to talk about an example of how we design an antagonist for the estrogen receptor. So just to remind you, the estrogen receptor is a so-called nuclear receptor, so lives in a cytoplasm. Upon binding to the ligand, it rearranges. So there's a helix called H12 binds above the binding site for estradiol. That causes dimerization, recruitment of this co-activator protein recruited to the AF2 regions, and that complex now migrates to the nucleus and initiates transcription. So how would look at the structure? So the pocket for estradiol contains a number of hydrophobic residues surrounding estradiol, and then it contains at the two extremes two areas where polar residues are found. And so we have here, let's put it in red, histidine, glutamate, and arginine, which make hydrogen contact with the phenol moiety on estradiol and with the alcohol moiety on the other end. And so these hydrogen bonding interactions serve to really orient the molecule in the pocket and kind of keep it in place. How do we design an antagonist? Well, we want to conserve the same interactions as much as possible. So raloxifene looks somewhat like estradiol. It contains a now 2-phenol moiety that makes the same kind of hydrogen bond contact here with the polar residues. They preserve some of the van der Waals interactions with the apolar residues here. And now, in addition, they also have, a side chain, which starts apolar and then ends up being polar, that kind of occupies a pocket that was not present when the receptor was bound to the estradiol ligand. And so basically, kind of squeeze it in, and by changing the conformation of the pocket prevents the response, the physiological response. So now basically helix 12 cannot dock above the binding site, and so we don't form the AF2 binding region, and so we can't bind the co-activator and initiate transcription.